Okay, so the next thing that we're going to do is called central limit theorem. And these problems are going to look very, very similar to the regular normal distribution problems. And in fact, they're worked pretty much the same way. So one of the first things that you're going to want to note is how do you tell the difference between a regular normal distribution problem and a central limit theorem problem, okay? So let's do an example and where we could start to see where that difference lies. Let's say the average GPA of students at a college is 2.20 with a standard deviation of 0.81. Okay? So let's say that's our given. The average GPA of students at a particular college is 2.20, and the standard deviation is 0.81. Okay, and again, somewhere in the problem, assume normal. Okay, I want to examine two questions. The first question is, let's say a randomly selected student is picked from this college, and what's the probability that person's GPA is over 3.0? Okay, so we're going to select one student randomly at the college. What's the probability? A student, some person that we randomly select, has a GPA of higher than 3.0. Okay, now talk me through how we would solve this problem. How would you solve this problem? It's exactly the same stuff we've been doing with regular normal distribution, right? You would draw a picture, the mean is 2.20, you go a little bit to the right where 3.0 is, and you want the area to the right of that. You transform that to a z standard normal distribution picture, figure out that area and look it up in your chart, and that would be the answer to this problem, okay? What if I change this problem a little bit and say, what's the probability? Instead of a single person, a class of 30 will have a mean GPA greater than 3.0. Okay? So question number one, we select some student from this college. What's the probability that student has a GPA higher than 3? All right, I solved that using regular normal distribution. This question, what's the probability a class of 30 that the mean of that class, okay, will have a GPA higher than 3? All right, we're going to do both of these problems. Which one do you think has a higher chance of happening?
The first one?
You think the first one has a better chance of happening?
No, I think the second one.
You think the second one has a better chance of happening? Okay, so let's think about this. We know for a fact that for all of the students on this campus, the mean is 2.20 for GPA, right? We're going to select one person from this campus. Okay, what's the probability that person has a GPA higher than 3.0? Okay, I'm not sure. Okay, but is the probability a single person has a GPA higher than 3.0 bigger than or smaller than a whole class of? I walk into a classroom of 30 students. I average that whole class, and I want to know if that average of that class, so that whole class, has an average higher than 3.0. Which one do you think has a better chance of happening? It should clearly be 1, okay? Because all of these students overall have a mean of 2.20. So if you take a whole class of 30 students, their mean should be going closer to 2.20. Is everybody with me on that? As opposed to if you just select one person, you have a better probability of that one person being higher than 3.0 than of the whole class having a mean higher than 3.0. Okay? All right, so this problem is a regular normal distribution problem, so let's go ahead and do that one. How do I do it? We've been doing them all day. So 2.20, we have 3.0, we want area to the right of 3.0. Transform that to a z standard normal. Draw that picture. Zero, z. And we want the area to the right of that z value. So that z value is going to be 3.0 minus 2.20 divided by 0.81. So grab your calculators and let's calculate that. If we round it off to 2 decimal places, we'll get 0.99, approximately 0.99 for my z value. So if I look up in my chart 0.99, you get 0.8389, and of course that's area to the left, and we want area to the right. So the answer is 1 minus 0.8389. So this area is 0.8389, and our area is 1 minus that. So 1 minus 0.8389. 0.1611, yes. So the answer to question number 1 is 1611. You have approximately a 16% chance a randomly selected student will have a higher GPA than 3.0. Okay? Okay, what the central limit theorem tells us is as we look at this problem, the mean of, if you took all classes of size 30 and you took the mean of those class means, does that make sense? So here's one class, we average out this class. Here's another class, we average out that class. There's another class. If you look at the mean of all of those individual means, it's going to be the same as the overall mean, okay? So that's one thing the central limit theorem tells us. The other thing is the standard deviation of all of those means is much smaller than the original standard deviation. And in fact, the standard deviation is going to be different. So when we get to my CLT, the mean of the sample means is the same as the overall mean, okay? But what's changed is the standard deviation is different. Your standard deviation is not just going to be this. It's going to be the original standard deviation divided by the square root of n, okay? So that formula you absolutely need to write down and have in your notes. So the way you solve this problem is exactly like we do regular normal, except the standard deviation is different. This is my formula for the standard deviation in doing a CLT problem, okay? All right, so let's do this problem. So the picture still looks the same. The original picture was 2.20. This picture, we want area to the right of 3.0. Okay? But when I transform this to a z using the CLT formula, this z value here, with the individual person, it was 0.99. But when we do a whole class of 30, okay, let's see what happens. So your formula is changed. It's going to be z equals your value minus the mean, 2.20, divided by, instead of just 0.81, it's 0.81 divided by the square root of 30. Okay? So your standard deviation is now 0.81, the original standard deviation, divided by the square root of how big your sample was, how big your class was in this case. Okay? Be super careful on this, guys. You have kind of a complex fraction here, so do this bottom part and separate it out from the numerator, and let's see what we get here. You should get about 5.41. Okay? So double check. You put this bottom part in parentheses, and this actually comes out to a z value of 5.41. Way out there to the right. Now, in fact, when I go to my book and I look at my table and I try to find the z-value of 5.41, what happens?
It's not there.
It's not there. And what does it say right under 3.4? What does it say? For z-values greater than 3.49, use 0.9999. Does everybody see that? So this z-value is so far to the right, it's off of the table here. Okay? So they're saying once you get past a certain point, you can go ahead and use this as 0.999, which means this value is very close to 0.0001. And in fact, it's smaller than that because we're even out further. Okay? So the original question, what has a better chance of happening? A single person having a GPA higher than 3.0, which had a 16% chance, or a whole class of 30, the mean of that class having a GPA higher than 3.0. It's almost close to 0. Okay. All right. When you guys are doing these problems, there should be some things that stand out. It's not a single person selected, it's a group. Okay, and in fact, that group has to have a size, because in our CLT, you need to know the square root of n. That is going to be the denominator of the standard deviation portion. Okay, so look at what you're looking at. Is it just a single individual thing, or is it a group of things? And how big is that group? And then it should say something about the mean of that sample, right? Because it doesn't make sense if I say a class of 30, what's the probability that class 3.0. That doesn't make sense. It has to be the average of that class. The average, or the average of the mean. Okay? The class sample mean. All right, let's do another one. The average hourly wage of a fast food worker is $5.55. All right. With a standard deviation of $1.15. All right. If a sample of 50 workers is selected, find the probability the mean of that sample will be between 525 and 590. If a sample of 50 workers is selected, what's the probability? And again, I'm about to underline this, the mean of that sample. Okay, if you see the phrase, the mean of that sample, within these normal distribution problems, that's pretty much screaming to you, this is a central limit theorem problem. Okay. What's the probability the mean of that sample is between 525 and 590? Okay. So here's our setup. We have a normal distribution. The mean is 555. The area we're looking for is between 525 and 590. So 525 is a little bit to the left over here. 590 is a little bit to the right. And I want to know this area between these two. Okay? I have to transform this to a z standard distribution, which has a mean of 0. And I have to figure out these two z values. We have one out here and one out here. Okay? But this is a central limit theorem question because it's asking the mean of a sample of 50 workers. Okay, so I don't just use the original z distribution formula, I use my central limit theorem z distribution formula. Okay, So this z-value here is going to be calculated by 590 minus 555 divided by the original standard deviation of $1.15 divided by the square root of 50. Okay. This is a CLT problem, and that's going to be your z-value for the right-hand side. Then you'll do the exact same work to get the z-value for 525. You'll do 525 minus 555 divided by that same standard deviation. Okay? So calculate those two z-values, and then once I have those, then finally the problem becomes find the area between two z-values. Okay? And then we'll be in the home stretch. So let's calculate these real fast. Be super careful with parentheses. So we have 5.9 minus 5.55, and then open up our parentheses when we do the division. And did you guys get about 2.15 for this one? So approximately 2.15 for the right z-value. And then let's do the left one. Approximately negative 1.84. So this one came out to about negative 1.84 if I rounded to 2 decimal places. All right, finally, once I get to this step, now it becomes a problem early in the chapter when I said, what's the area between 2.15 and negative 1.84? Okay, so you just look that up in your charts. And again, I can't overstress how good you have to be about finding areas in the normal distribution. All right. So if I look at 2.15, you get 9842. So this whole area from here over is 9842. And then I need to subtract off, looking up negative 1.84. You get 0329. So this is 0329. So finally, my answer to this problem is 9842 minus 0329. (9513). Central limit theorem. Okay. A group of 50. What's the probability the mean of that group is blah blah blah. Okay. That's a central limit theorem problem. If it was a single fast food worker is selected, what's the probability that fast food worker earns between blah blah blah? That's regular normal distribution. Okay. So you have to be really clear as to if you're doing regular normal or central limit theorem. All right. Any questions? Okay.